in this lecture you'll find out the length of line segment X in the drawing we have two quarter circles. These two quarter circles touch each other here at point B. In addition, we know that line segment AB equals to 1 unit in its length, and also we know that line segment QS equals to line segment SP, and our mission is to find out the length of this line segment BC, that is equal to X. Okay, so first of all, AB is equals to PA in this quarter circle, side AB equals to side AP. They are both the radii of this quarter circle, therefore they are equal to each other. But side AB equals to 1, therefore side AP will be also equal to 1. Likewise, in the this big quarter circle, side BC equal to side QC. They are both the radii of this quarter circle, therefore they are equal to each other. But side BC equals to X, therefore side QC will be also equal to X. In the next step, I will copy the right triangle PAC. In the next step, we will join points P and B together by a straight line. And we join points Q and B together by a straight line. In the next step, I'll copy the right triangle PAB to a new page and we'll implement the Pythagoras theorem in this right triangle PAB. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle PAB that I call it from the original drawing. Side PA equals to 1 unit, and side AB also equals to 1 unit. In this right triangle PAB, according to the Pythagoras theorem, PA square, PB square, that is the square of the hypotenuse, equals to PA square plus AB square. So PB square equals to PA square. PA is 1, therefore PA square is 1 square, that is 1, plus AB square. AB is also 1, therefore AB square is 1 square, that is 1. So in total PB square equals to 1 plus 1, that is 2. PB square equals to 2. We take out of this equation and we get that PB, the length of the hypotenuse PB, is actually equals to the square root of 2 units. So we can write down in the original drawing that the hypotenuse PB equals to the square root of 2 units in its length. Likewise, I copy the right triangle QCB in the new page and we'll implement on this right triangle QCB the Pythagoras theorem. again by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle QCB that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle QCB, QB squared, the square of the hypotenuse, equals to QC squared plus BC squared. So QB squared equals to QC squared. QC is x, therefore QC squared is x squared plus BC squared. BC is also x, therefore BC squared is x squared. So in total, QB squared equals to x squared plus x squared, that is 2x squared. QB squared equals to 2x squared. Here we take a root out of this equation, and we get that QB equals to the square root of 2 times x squared. That is to say, QB equals to the square root of 2, and the square root of x squared is x. So in total, QB equals to the square root of 2 times x units in its length. So you can write down in the original drawing that QB, the hypotenuse QB of the right triangle QBC equals to the square root of 2 times x units in its length. In the next step, we focus on the right triangle PAB. In the right triangle PAB, those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that also must be equal to each other. So if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in triangle PAB must be equal to 180 degrees. So which angles we have inside triangle PAB? We have, this is angle alpha, plus alpha is 2 alpha plus 90 degrees. In total, the sum of those three angles must be equal to 180 degrees. So 2 alpha plus 90 degrees must be equal to 180 degrees. Repeat again. The sum of the angles in the right triangle PAB must be equal to 180 degrees. That is say 2 alpha plus 90 degrees equals to 180 degrees. We subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. We divide this equation by 2, and we get that alpha equals to 90 degrees over 2, that is 45 degrees. So actually, this is angle alpha that equals to 45 degrees in its size. And this is also angle alpha that equals to 45 degrees. If we repeat on the same process on the right triangle QCB, here in the right triangle QCB, side QC also equals to side CB. So we will arrive to the same results, that this angle equals to 45 degrees and this angle also equals to 45 degrees. In the next step, I present to you rule number 3, and we will implement rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equals to 180 degrees. So in the drawing we have this is the straight line AB. If we focus on the upper side of this straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to this rule number 3. So which angles we have in the upper side of AB at point Q? We have this angle that is alpha and the other angle that is beta. So in total alpha plus beta must be equal to 180 degrees according to this rule number 3. Actually you can implement rule number 3 in our drawing. Why? Because in our drawing if we focus on the upper side of this straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So I'll copy the straight line AC with point B on it on a new page, and we will implement rule number 3 in this straight line AC. So actually, this is the straight line AC that I copied from the original drawing. According to rule number 3, the sum of the angles in the upper side of this straight line AC at point B must be equal to 180 degrees. So which angles we have in the upper side of AC at point B? We have this angle that is 45 degrees, plus this missing angle that we will define as X, plus this angle that is 45 degrees. So in total, the sum of those three angles must be equal to 180 degrees according to rule number 3. So 45 degrees plus 45 degrees is 90 degrees. So in total, in this side of the equation, we have 90 degrees plus X equals to 180 degrees. Here we subtract 90 degrees from this equation, and we'll get that the missing angle X equals to 180 degrees minus 90 degrees, it is 90 degrees. So the missing angle is the right angle, it is equals to 90 degrees. So you can write down in the original drawing that the missing angle PBQ is equals to 90 degrees in its size. So it is a right angle. And therefore, triangle PBQ is a right triangle. In the next step, I will copy the right triangle PBQ in a new page, and we will block this right triangle by a circle. We have a rule that any triangle can be blocked by a circle. Okay? So actually, this is the right angle PBQ that I covered from the original drawing, and I block this right angle PBQ by this circle. So in the drawing we have peripheral angle PBQ. This peripheral angle PBQ is equals to 90 degrees in its size. So I write it down. Peripheral angle PBQ is equals to 90 degrees in its size. It is a right angle. And we have rule number 5 that relates to any peripheral angle that is a right angle that is equals to 90 degrees in its size. According to rule number 5, any peripheral angle that is equal to 90 degrees must be subtended on the diameter of the circle. So in the drawing we have a circle. Inside this circle we have this peripheral angle MAN. This peripheral angle MAN, it is a right angle. It is equals to 90 degrees in its size, and therefore according to this rule number 5, peripheral angle MAN must be subtended on the diameter of the circle. That is to say, MN is the diameter of the circle. So any peripheral angle that is a right angle must be subtended on the diameter of the circle. Actually, you can implement rule number 5 in our drawing. Why? Because in our drawing we have, this is peripheral angle QPP or PBQ that is equals to 90 degrees in its size. Therefore, according to rule number 5, peripheral angle PBQ is subtended on the diameter of the circle. That is to say, PQ is the diameter of the circle. PQ is the diameter of this circle. So if we define the radius of this circle as R, then the diameter PQ must be equal to R. Okay? The diameter PQ of this circle equals to R from one side, but from the other side, in the drawing, it is given us the question that QS equals to SP. So if QS is X, then SP must be also equal to X because they are equal to each other. So in total, the length of this line segment PQ, it is equals to PQ equals to PS plus SQ. That is to say, PQ equals to PS, that is X, plus SQ, that is also X. So in total, PQ equals to X plus X, that is 2X. So PQ equals to 2X from one side. From the other side, we found out that PQ is the diameter of this circle, therefore it is equals to R. So from the other side, PQ equals to R, and from those two equations, PQ equals to 2X and PQ equals to 2R, we will derive that 2x equals to 2r. 2x equals to 2r. Here we'll divide this equation by 2. And finally, we'll get that x equals to r. X equals to r. So here, PS that is equals to x, it is equals to r. And SQ that is equal to x, it is also equals to r. In the next step, I will copy point S is located on PQ. So I will copy point S to the new drawing exactly where it is located at line segment PQ. So I copy point S from the original drawing to our new drawing here exactly where it is located on line segment PQ. So this is point S that I copied from the original drawing to exactly to the same point on PQ where it is located in this original drawing. So we just right now found out that PS equals to R, PS equals to R, and SQ also equals to R. SQ also equals to R. So actually at point S, those two radii of this circle touch each other. Why? Because the radius PS starts from point P and ends at point S, and the radius QS starts from point Q and ends at point S. So those two radii touch each other at point S. Therefore, point S is the center of this circle. So you can write down that here that point S is the center of the circle. In the next step, we'll join points S and B together by a straight line. Point S is the center of the circle. Point B is the point on the circle itself. Therefore, SB is the radius of this circle that is equals to R. So in conclusion, you can say that PS equals to SQ equals to SB. All the radii of this circle, therefore they are equal to each other. In the original drawing, we'll also join points S and B together by a straight line. SB is the radius of the previous circle that is equal to R. So here, PS equals to SQ equals to SB. All the radii of the previous circle, therefore they are equal to each other. And especially SB equals to SQ. Okay? So, in the next step, I'll copy the big quarter circle to a new page, and then we'll complete this big quarter circle to a circle. So actually, this is the big quarter circle that I copied from the original drawing. This angle equals to 90 degrees because it is a quarter circle. And we have already found out that SB equals to SQ. They are both the radii of the previous circle, therefore they are equal to each other. Now I'll complete this quarter circle to a circle. So I completed the quarter circle to a circle. In the next step, I present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 13. According to rule number 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ACB. This peripheral angle ACB is equal to theta in its size, and it is subtended on arc AB. In addition, inside this circle we have the central angle AOB. This central AOB is also subtended on the same arc, arc AB. Okay, so in the drawing we have two angles that both of them are subtended on the same arc, arc AB. And therefore, the central angle AOB will be twice as large as the peripheral angle ACB that is subtended on the same arc, arc AB. And because of the fact that the peripheral angle ACB equals to theta, then the central angle AOB will be equal to 2 theta. So the central angle is always twice as large as the peripheral angle that is subtended on the same arc. You can actually implement rule number 13 in our drawing. Why? Because in our drawing we have this peripheral angle BSQ. This is the peripheral angle BSQ. Peripheral angle BSQ is subtended on arc QB. Again, peripheral angle BSQ is subtended on arc QB. And we have also the central angle QCB. This is the central angle QCB that is subtended on the same arc, arc QB. Again, the central angle QCB is subtended on the same arc, arc QB. Therefore, according to rule number 13, this central angle QCB must be twice as large as the peripheral angle QSB that is subtended on the same arc, arc QB. Now we have to find out what is the size of the central angle QCB. What is the size of this central angle QCB? We'll find out the size of this angle according to a new rule. It is actually rule number 6. According to rule number 6, the sum of the angles around any point will be equal to 360 degrees. Again, the sum of the angles around any point are equal to 360 degrees. Okay, so in the drawing we have, this is point A, and according to this rule, rule number 6, the sum of the angles around this point, point A, must be equal to 360 degrees. In order to prove that this rule is true, I drew this straight line. This straight line passed through point A. Now we can implement here rule number 3. According to rule number 3, the sum of the angles on one side of a straight line is equal to 360 degrees. That is to say, the sum of the angles on the upper side of this straight line at point A equals to 180 degrees, and the sum of the angles on the lower side of this straight line equals to the sum of the angles on the lower side of this straight line at point A is also equal to 180 degrees. So in total, the sum of the angles in the upper side of this straight line at point A is 180 degrees, plus the sum of the angles in the lower side of this straight line at point A is also 180 degrees. So in total, the sum of the angles around point A is 180 degrees plus 180 degrees, that is 360 degrees, exactly according to this rule. Rule number 6 that says that the sum of the angles around any point is equal to 360 degrees. Okay, so I can actually implement rule number 6 in our drawing. Why? Because in our drawing, if you focus at this point C, according to rule number 6, the sum of the angles around point C must be equal to 360 degrees. So which angles we have around point C? We have this angle that is a right angle plus this missing angle. In total, they must be equal to 360 degrees according to rule number 6. Therefore, this missing angle must be equal to 270 degrees. In order to complete the sum of the angles around point C to 360 degrees, the missing angle here must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees, it is 360 degrees. Exactly according to rule number 6. So the missing angle equals to 270 degrees. The missing angle, it is actually the central angle QCB. So the central angle QCB equals to 270 degrees. Therefore, the peripheral angle BSQ that is subtended on the same arc RQB must be equal to half of it. That is to say, it must be equal to 270 degrees over 2, that is 135 degrees. So the peripheral angle QSB equals to 135 degrees in its size. Okay, we will continue to focus here on triangle BSQ. Triangle BSQ is an isosceles triangle. Why? Because side BS equals to side SQ. Those two sides, they are both the radii of the previous circle, therefore they are equal to each other. So triangle BSQ is an isosceles triangle, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the isosceles triangle BSQ. So which angles we have in the isosceles triangle BSQ? We have alpha plus alpha, that is 2 alpha. 2 alpha plus this angle that is 135 degrees. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned, that the sum of the angles in any triangle is equal to 180 degrees. We subtract 135 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 135 degrees is 45 degrees. We divide this equation by 2, and finally we get that alpha equals to 45 over 2 degrees. Okay, so this again alpha equals to 45 over 2 degrees, and this again alpha also equals to 45 degrees in its size. You can write down in the original drawing, angle SQB equals to 45 over 2 degrees. This is angle SQB that is equal to 45 over 2 degrees. Okay. In the next step, I will copy the right triangle PBQ in a new page, and we will analyze this right triangle, triangle PBQ. Side PB of the right triangle PBQ is equal to the square root of 2 units in its length. Side QB equals to the square root of 2 times x units. And this angle equals to 45 over 2 degrees. So actually, this is the right triangle PBQ that I copied from the original drawing. Again, side PB equals to the square root of 2 units, side QB equals to the square root of 2 times x units, and this is again alpha, this is equal to 45 or 2 degrees. So in this right triangle PBQ, tangents 45 over 2 degrees is equals to PB over BQ. Again, tangents 45 over 2 degrees equals to PB over BQ. Okay. PB equals to the square root of 2 units, and BQ equals to the square root of 2 times x units. So here we have square root of 2 in the numerator and square root of 2 in the denominator, so square root of 2 will get cancelled, and we're left only with 1 over x. In conclusion, found out that according to equation number 1, tangents 45 over 2 degrees equals to 1 over x. So I write it down. According to equation number 1, we found out that tangents 45 over 2 degrees equals to 1 over x. We have the trigonometric identity that tangents 2 theta equals to 2 times tangents theta over 1 minus tangents square theta. Okay? Again, tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. We'll define theta as 45 over 2 degrees, and therefore 2 theta will be equal to 45 degrees, of course. Now we'll substitute theta in this trigonometric identity by 45 over 2 degrees, and we substitute 2 theta by 45 degrees. And we get, this will be equation number 2, that tangents 2 theta according to our definition is 45 degrees, so it is tangents 45 degrees, that is equals to 2 times tangents theta, and theta according to our definition is 45 over 2 degrees over 1 minus tangents square theta, and theta according to our definition is 45 over 2 degrees. So in conclusion, we found out that according to equation number 2, tangents 45 degrees equals to 2 times tangents 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. Okay, in the next step, we will define tangents 45 over 2 degrees as t. Again, tangents 45 over 2 degrees equals to t according to our definition, and we will substitute tangents 45 over 2 degrees in this equation, equation number 2, by t. Okay, and we'll get that according to equation number 2, tangents 45 degrees is 1, and it is equals to 2 times tangents 45 over 2 degrees. Tangents 45 over 2 degrees is t, so we substitute tangents 45 over 2 degrees by t. So in total, in the numerator we have, in this side of the equation, in the numerator we have 2t. Okay, so 1 equals to 2t over, in the denominator of this side of the equation we have 1 minus tangent square 45 over 2 degrees. If tangents 45 over 2 degrees equals to t, it means that tangent square 45 over 2 degrees will be equal to t squared. So in total, in the denominator, we will have 1 minus t squared. Here in the denominator, we have 1 minus t squared. Here we multiply this equation number 2, by 1 minus t squared. And we get that according to equation number 2, 1 minus t squared equals to 2t. Here we add to this equation number 2, t squared. And we get that according to equation number 2, t squared plus 2t equals to 1. Here we subtract 1 from this equation number 2, and we get that according to equation number 2, according to equation number 2, t squared plus 2t minus 1 equals to 0. So, equation number 2, t squared plus 2t minus 1 equals to 0 is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Okay. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. And the variable that we are looking for in this specific quadratic equation is t. So x equals to t. So we'll put the data inside this formula for x, and we find out the value or the values of t because x equals to t. So now we substitute x by t, and we get that here x is t, and it is equals to minus b. b is 2, therefore minus b is minus 2, plus minus square root of b squared. b is 2, therefore b squared is 2 squared, that is 4, minus 4 times a is 1, times c, that is minus 1. All divided by 2 times a. A is 1, so it is 2 times 1. So t equals to minus 2 plus minus. Inside the root we have minus 4 times minus 1 is plus 4, and 4 plus 4 is 8. So inside the root we left only with 8 divided by 2. In conclusion, we found out that the solution to our specific quadratic equation is t equals to minus 2 plus minus square root of 2 over 2. So t equals to minus 2 plus minus square root of 8. 8 is 4 times 2, so we substitute 8 by 4 times 2 divided by 2. So t equals to minus 2 plus minus the square root of 4 is 2, so inside the root we left only with 2, all divided by 2. In conclusion, found out that t equals to minus 2 plus minus 2 times square root of 2 over 2. So t equals to minus 2 over 2 is minus 1, plus minus 2 over 2 is 1, so in total this expression equals to square root of 2. So in conclusion, we found out that t equals to minus 1 plus minus square root of 2. So here we will have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2. And the second solution that is possible for t is that t equals to minus 1 plus square root of 2. According to the first solution, t equals to minus 1 minus 2. Minus 1 minus square root of 2 is a negative number, therefore t is a negative number. On one side, but from the other side, according to our definition, t equals to 45 over 2 degrees. Again, t equals to tangents 45 over 2 degrees. That is a positive number. So t, according to our definition, t is a positive number. So t cannot be simultaneously a negative number and a positive number, so we got to a contradiction. Therefore, the first solution is a correct solution. We cancel this solution and we left only with the second solution that is possible for t, that t equals to minus 1 plus square root of 2. That is to say, t equals to, we change the numbers, the order of the numbers here, t equals to square root of 2 minus 1. A plus b equals to a minus b. A plus b equals to b plus a. Therefore, we can change the order of the numbers here. And according to our definition, t equals to tangents 45 over 2 degrees. So for one side, t equals to tangents 45 over 2 degrees. But from the other side, according to this second solution, t equals to square root of 2 minus 1. So this equation number 2 states that t equals to t. Because from one side t equals to tangents 45 over 2 degrees, but from the other side t also equals to the square root of 2 minus 1. So t equals to t. This is according to equation number 2. While according to equation number 1, we have already found out that tangents 45 over 2 degrees equals to 1 over x. Here I show you. We have already found out that according to equation number 1, tangents 45 over 2 degrees equals to 1 over x. Here tangents 45 over 2 degrees equals to 1 over x. And tangents 45 over 2 degrees equals also to square root of 2 minus 1. So we have two different equations or expressions from tangents 45 over 2 degrees. Therefore, we create equation number 3 that states that tangents 45 over 2 degrees, according to equation number 1, must be equal to tangents 45 over 2 degrees, according to equation number 2. Again, according to equation number 3, tangents 45 over 2 degrees, according to equation number 1, must be equal to tangents 45 over 2 degrees according to equation number 2. So according to equation number 3, we actually found out that tangent 45 degrees according to equation number 1 is 1 over x, and it must be equal to tangent 45 degrees according to equation number 2, that is actually square root of 2 minus 1. So according to equation number 3, we actually found out that 1 over x equals to the square root of 2 minus 1. Here we multiply this equation number 3 by x, and we get that according to equation number 3, 1 equals to square root of 2 minus 1 times x. Here we divide this equation number 3 by square root of 2 minus 1, and we get that according to equation number 3, x equals to 1 over square root of 2 minus 1. So I actually found out that x equals to 1 over square root of 2 minus 1. Okay, so here we'll multiply this side of the equation by square root of 2 plus 1, and then we'll divide it by square root of 2 plus 1. Square root of 2 plus 1 over square root of 2 plus 1 is 1, and it is allowable to multiply anything by 1. You don't change the value of the expression when you multiply it by 1. Therefore this operation is allowable. So we multiplied this side of the equation by square root of 2 plus 1, and then we divide it by square root of 2 plus 1, and found out actually that x equals, in the numerator we have square root of 2 plus 1 over this expression square root of 2 minus 1 times square root of 2 plus 1 will be equal to, we use the algebraic identity, that a plus b, a minus b times a plus b equals to a square minus b square. According to this algebraic identity, a minus b times a plus b equals to a square minus b square, we get that this expression square root of 2 minus 1 times square root of 2 plus 1 will be equal to the square root of 2 squared, that is 2, minus 1 squared, that is 1, so it is minus 1. So in total this expression equals to 2 minus 1, that is 1. So in conclusion, we found out that x equals to the square root of 2 plus 1 over 2 minus 1 is 1, and square root of 2 plus 1 over 1 is square root of 2 plus 1. So x equals to square root of 2 plus 1 units in its length. On terms of numbers, it is equals to 2.414 units. And that is the answer to the question. I'll repeat again. The length of this line segment BC is equal to x. This equals to either square root of 2 plus 1 units, or in terms of numbers, BC is equal to x. This equals to 2.414 units. A little bit less than 2.5 units. Okay, so in the next step, I'll summarize the lecture. In this lecture, we found out the length of this line segment BC that is equal to x. In the drawing, we have two quarter circles. Those two quarter circles touch each other here at point B. In addition, we know that side AB equals to 1 unit in its length, and also we know that QS equals to SP. Our mission is to find out the length of this line segment BC that is equal to x. Okay, so this is a quarter circle, and therefore side AB must be equal to side AP. Why? Because both of those two sides are the radii of this quarter circle, therefore they are equal to each other. But side AB equals to 1, therefore side PA must be also equal to 1. Likewise, this is a quarter circle, and therefore side QC must be equal to side CB, because both of them are the radii of this quarter circle, therefore they are equal to each other. But BC equals to x, therefore QC must be equal to x. Then we join points P and B together by straight line, and we join points Q and B together by straight line. Then I copied the right triangle PAB in a new page, and we implemented the Pythagoras theorem in this right triangle PAB. Actually, this is the right triangle PAB that I copied from the original drawing. In this right triangle PAB, by PT is evaluation for Pythagoras theorem. According to the Pythagoras theorem, PB square equals to PA square plus AB square. So PB square, that is the square of the hypotenuse, equals to PA square. PA is 1, therefore PA square is 1 square, that is 1, plus AB square. AB is 1, therefore AB square is 1 square, that is 1. So in total PB square is 1 plus 1, that is 2. So PB square equals to 2. We took out of this equation and finally found out that the length of the hypotenuse PB equals to the square root of 2. So we can write down here that PB equals to the square root of 2 units in its length. Then I copied the right triangle QBS in a new page and implemented the Pythagoras theorem in this right triangle QBC. The right triangle QBC. So this is the right triangle QBC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle QBC, QB square equals to QC square plus BC square. So QB square, that is the square of the hypotenuse, equals to QC square. QC is x, therefore QC square is x square plus BC square. BC is x, therefore BC square is also x square. So in total QB square equals to x square plus x square, that is 2x square. So QB square equals to 2x square. We took a root out of this equation and finally found out that QB equals to the square root of 2 times x square. That is to say, QB equals to the square root of 2, and the square root of x square is x. So in total, QB equals to the square root of 2 times x. QB equals to the square root of 2 times x. So we can write here that QB equals to the square root of 2 times x. Okay, then we focused on the right triangle PAB. In the right triangle PAB, side PA equals to side PB. Side PA equals to side AB. And we have the rule that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides, we will have those two angles that must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha. And we also know that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the right triangle PAB. So which angles we have in the triangle PAB? We have alpha plus alpha, that is 2 alpha plus 90 degrees. In total, they must be equal to 180 degrees according to the rule that I mentioned. In the right triangle PAB, 2 alpha plus 90 degrees must be equal to 180 degrees. We subtracted 90 degrees from the equation and finally found out that 2 alpha equals to 180 degrees minus 90 degrees. It is 90 degrees. Here we divided this equation by 2 and found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is the angle alpha that is equal to 45 degrees in its side. This is also angle alpha that is equal to 45 degrees. Now we have the other triangle, the right triangle that is also an isosceles triangle. If we repeat on the same process in this right triangle QCB, we'll get to the result that those two angles, each of them, is equals to 45 degrees. Okay? It's very easy to do it. Then I presented to you rule number 3 and implemented rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So in the drawing we have the straight line AB. If we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to this rule number 3. So which angles we have at the upper side of AB at point Q? We have this angle alpha and the other angle that is beta. So in total alpha plus beta must be equal to 180 degrees according to this rule number 3. So we can actually implement rule number 3 in our drawing. Why? Because in our drawing we have the straight line AC. If we focus on the upper side of this straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So we copy the straight line AC with point B in a new page and we implemented rule number 3 in this straight line AC. This is the straight line AC that I copied from the original drawing. This is point B. So according to rule number 3, the sum of the angles in the upper side of this straight line AC at point B must be equal to 180 degrees. So which angles we have at the upper side of AC at point B? We have this angle that is 45 degrees plus the missing angle that we define as x plus this angle that is 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. 45 degrees plus 45 degrees is 90 degrees. So in this side of the equation, we have 90 degrees plus x. That is equal to 180 degrees. We subtracted 90 degrees from this equation and finally found out that x, the missing angle x, equals to 180 degrees minus 90 degrees, that is 90 degrees. So actually, angle PBQ, that is the missing angle x, equals to 90 degrees in its size, and therefore triangle PBQ is a right triangle. So I copied the right triangle PBQ in a new page, and we blocked this right triangle PBQ by a circle. We have the rule that any triangle can be blocked by a circle. So this is the right triangle PBQ that I blocked by this circle. So in the drawing we have peripheral angle PBQ that is equal to 90 degrees. And we have here rule number 5 that relates to any peripheral angle that is a right angle. According to rule number 5, any peripheral angle that is equal to 90 degrees must be subtended on the diameter of the circle. In the drawing we have a circle. Inside this circle we have this peripheral angle MAN. This peripheral angle MAN is a right angle that is equal to 90 degrees in its size. Therefore, according to this rule number 5, this peripheral angle MAN must be subtended on the diameter of the circle. That is to say, MN is the diameter of the circle. So in conclusion, we can say that because of the fact that peripheral angle MAN is equal to 90 degrees, therefore it is subtended on the diameter of the circle. MN is the diameter of the circle. We can implement rule number 5 in our drawing. In our drawing, we have this peripheral angle PBQ. That is a right angle that is equal to 90 degrees in size. Therefore, peripheral angle PBQ is subtended on the diameter of the circle. That is to say, PQ is the diameter of the circle. Okay, so according to rule number 5, PQ is the diameter of the circle. PQ is the diameter of the circle. So if we define the radius of this circle as r, then the diameter PQ must be equal to 2r. That is from one side. But from the other side, we have, it is given us the equation that PS equals to SQ. So if PS is x, then SQ must be also equal to x because they are equal to each other. So what is the length of PQ? PQ equals to PS plus SQ. That is to say, PQ equals to PS, that is x, plus SQ, that is also x. So in total, PQ equals to x plus x, that is 2x. So here, we actually found out that PQ equals to 2x from one side, but from the other side, PQ is also the diameter of this circle, and according to rule number 5, therefore PQ equals to 2r. repeat again. From one side, PQ equals to 2x. From the other side, PQ also equals to 2r. It is the diameter of the circle. So from those two equations, equation number 1 and equation number 2, we derive that 2x equals to 2r. We divided this equation by 2 and finally found out that x equals to r. So we can write here that x equals to r, PS that is equals to x equals to r, and SQ that is equal to x equals to r. Then I copied point S from the original drawing from here. Point S is located on PQ. I copied point S from this original drawing to our new drawing, exactly where it is located on PQ. To the same location. I copied point S from the original drawing here in the new drawing. Okay, now we actually found out that PS equals to R, PS equals to R, and QS also equals to R. QS also equals to R. So PS and QS, they are both the radii of this circle, and they touch each other here at point S. And because of the fact that those two radii touch each other at point S must be the center of the circle. Okay, so can write down here that point S is the center of the circle. Then we join points S and B together by a straight line. Point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of this circle that is equal to R. Okay, so here I join points S and B together by a straight line. SB is the radius of the circle that is equal to R. So in conclusion, I found out that PS equals to SB equals to SQ. They are all the radii of this circle, therefore they are equal to each other. Then I copied this quarter circle to a new page, and then we completed this quarter circle to a circle. This is the quarter circle that I copied from the original drawing. This angle equals to 90 degrees because it is a quarter circle. We have already found out that SB equals to SQ. All the radii, they're both the radii of the previous circle, therefore they are equal to each other. And then I completed this quarter circle to a circle. Then I presented to you rule number 13, and we implemented rule number 13 in our drawing. According to rule number 13, a certain angle is twice as large as the peripheral angle subtended on the same arc. In the drawing we have this circle. Inside this circle we have peripheral angle ACB. This peripheral angle ACB equals to theta in its size, and it is subtended on arc AB. In addition, in this drawing we have the central angle AOB. This central angle AOB is subtended on the same arc AB. And therefore, the central angle must be twice as large as this peripheral angle ACB. Why? Because both of them, they are both subtended on the same arc AB. And because of the fact that the peripheral angle ACB equals to theta, then the central angle AOB that is subtended on the same arc must be equal to 2 theta. Okay, so the central angle will be twice as large as the peripheral angle that is subtended on the same arc. We can actually implement rule number 15 in our drawing. Why? Because in our drawing we have the peripheral angle BSQ, that is, this peripheral angle BSQ is subtended on arc QB. This is the central angle BSQ that is subtended on arc QB. And we have also the central angle QCB. This is the central angle QCB. This is the size of the angle. The central angle QCB is also subtended on the same arc QB. Therefore, according to rule number 13, the central angle QCB must be twice as large as the peripheral angle PSQ that is subtended on the same arc RQB. Okay, now we have to find out what is the side of the central angle QCB. This is the angle. In order to find out the size of the central angle QCB, I presented to you rule number 6, and we implemented rule number 6 in our drawing. According to rule number 6, the sum of the angles on the sum of the angles around any point is equal to 360 degrees. In the drawing we have this point A. According to this rule number 6, the sum of the angles around point A must be equal to 360 degrees. In order to prove that this rule is true, I drew a straight line that passes through point A. Now we can implement here rule number 3. According to rule number 3, the sum of the angles on the upper side of this straight line point A equals to 180 degrees, and the sum of the angles in the lower side of this straight line at point A must be also equal to 180 degrees. Therefore, in total, the sum of the angles in the upper side at point A of this straight line and then in the lower side of this straight line at point A is equal to 180 degrees plus 180 degrees, that is 360 degrees. That is to say, the sum of the angles around point A in total it is equal to 360 degrees, exactly according to this rule number 6 that states that the sum of the angles around any point must be equal to 360 degrees. Now we can implement rule number 6 in our drawing. Why? Because in our drawing we have, if we focus at point C, according to rule number 6, the sum of the angles around point C must be equal to 360 degrees. So which angles we have around point C? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 360 degrees. Therefore, the missing angle here must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees, it is 360 degrees. That is the sum of the angles around point C according to rule number 6. Therefore, the missing angle here is equal to 270 degrees. That is to say, the central angle QCB equals to 270 degrees. And therefore, according to rule number 13, the peripheral angle PSQ that is subtended on the same arc RQB as the central angle must be equal to half of it. That is to say, it must be equal to 270 degrees over 2, that is 135 degrees. So angle PSQ equals to 135 degrees in its size. Then we focus on triangle BSQ. In triangle BSQ, side BS equals to side SQ. Both the radii of the previous circle, therefore they are equal to each other. So here, therefore it is an isosceles triangle, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha, because they are equal to each other. And we know that the sum of the angles in any triangle is equal to 180 degrees. And especially it is true in the isosceles triangle BSQ. In the isosceles triangle BSQ, alpha plus alpha is 2 alpha plus 135 degrees. In total, they must be equal to 180 degrees. We subtracted 135 degrees from this equation and found out that 2 alpha equals to 180 degrees minus 135 degrees is 45 degrees. 2 alpha equals to 45 degrees. We divided the equation by 2 and finally found out that alpha equals to 45 over 2 degrees. This is angle alpha that is equal to 45 over 2 degrees, and this is also angle alpha that is equal to 45 over 2 degrees in its size. Then I copied the right triangle PBQ in a new page and we analyze this right triangle PBQ. Side PB equals to the square root of 2 units, side BQ equals to the square root of 2 times x units, and this is angle alpha that is equals to 45 over 2 degrees. I repeat again. Side PB equals to the square root of 2 units, side BQ equals to the square root of 2 times x, and this is angle alpha that is equal to 45 over 2 degrees. In the right triangle PBQ, times 45 over 2 degrees equals to the square root of equals to PB over BQ. Again, times 45 over 2 degrees equals to PB over BQ. PB is square root of 2, BQ is square root of 2 times x. So we have square root of 2 in the numerator and square root of 2 in the denominator, so square root of 2 will get cancelled, and we left only with 1 over x. So in conclusion, we found out that according to equation number 1, times 45 over 2 degrees equals to 1 over x. Here, times 45 over 2 degrees equals to 1 over x. And we have the trigonometric identity that tangent 2 theta equals to 2 tangent theta over 1 minus tangent square theta. Then we defined theta is 45 over 2 degrees. If theta is 45 over 2 degrees, then 2 theta must be also, of course, equals to 45 degrees. Then we substitute theta, this trigonometric identity, by 45 over 2 degrees, and we substitute 2 theta by 45 degrees. And we found out here that tangent 2 theta is 45 degrees according to our definition, so it is tangent 45 degrees equals to 2 times tangent theta. And theta is 45 over 2 degrees according to our definition, so it is 2 times 45 over 2 degrees over 1 minus tangent square 45 tangent square theta. And theta is 45 over 2 degrees, so it is 1 minus tangent square 45 over 2 degrees. So in conclusion, found out that according to equation number 2, times 45 degrees equals to 2 times tangent 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. Then we define tangent 45 over 2 degrees as t, and we substituted tangent 45 over 2 degrees in this equation number 2 by t. And found out that according to this equation number 2, tangent 45 degrees is 1, and it is equals to 2 times tangent 45 over 2 degrees, and tangent 45 over 2 degrees according to our definition is t, so it is 2t over 1 minus tangent square 45 over 2 degrees. If tangent 45 over 2 degrees is t, then tangent square 45 over 2 degrees will be equal to t square. So in total, in the denominator, we have 1 minus t square. 1 minus t square. So in conclusion, we found out that according to equation number 2, 1 equals to 2t over 1 minus t square. Here we multiply this equation number 2 by 1 minus t square, and found out that according to equation number 2, 1 minus t square equals to 2t. We added to this equation number 2 t square, and found out that t square plus 2t equals to 1. We subtracted from this equation number 2 1, and found out that t square plus 2t minus 1 equals to 0. This is the quadratic equation, and the general formula for quadratic equation is ax squared plus bx, ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of a quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula: x equals to minus b plus minus square root of 2. Again, x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. And the variable that we are looking for in this quadratic equation is t, so x equals to t. We put the data inside the formula for x and found out the value of the values of t, because here x equals to t, therefore we substitute x by t, and found out that x equals to minus b, b is 2, so 1 minus b is minus 2, plus minus square root of b squared. B is 2, therefore b squared is 2 squared, that is 4. Minus 4 times a is 1, times c, that is minus 1. Divided by 2a. A is 1, so it is 2 times 1. So inside the root we have minus 4 times minus 1 is plus 4, and 4 plus 4 is 8. So in total, inside the root we left only with 8. And we found out actually that t equals to minus 2 plus minus, inside the root we left only with 8 over 2. So t equals to minus 2 plus minus, 8 is 4 times 2 over 2. So t equals to the square root of t equals to minus 2 plus minus, the square root of 4 is 2. So inside the root we left only with 2 divided by 2. So t equals to minus 2 plus minus 2 times square root of 2 over 2. So t equals to minus 2 over 2 is minus 1, and 2 over 2 is 1, so in total this expression equals to the square root of 2. In conclusion, found out that t equals to minus 1 plus minus square root of 2. So here we have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus 2, and the second solution that is possible for t is that t equals to minus 1 plus square root of 2. According to the first solution, according to the first solution for t equals to minus 1 minus square root of 2. Minus 1 minus square root of 2, it is a negative number. So t is a negative number, because t equals to minus 1 minus square root of 2 from one side. But from the other side, according to our definition, t equals to times 45 over 2 degrees, that is a positive number. So t is a positive number. T cannot be simultaneously a negative number and a positive number. So we have a contradiction. So this solution is incorrect solution, and therefore we left only with the second solution that is possible for t, that t equals to minus 1 plus square root of 2. A plus b is b plus a, so we can change the order here. T equals to the square root of 2 minus 1 from one side, but from the other side, t equals to, according to our definition, t equals to times 45 over 2 degrees. So from one side, t equals to times 45 over 2 degrees. From the other side, t equals to the square root of 2 minus 1. So equation number 2 states that t equals to t. So according to equation number 2, we actually found out that times 45 over 2 degrees equals to the square root of 2 minus 1 from one side. But from the other side, according to equation number 1, we have already found out that times 45 over 2 degrees equals to 1 over x. Here, we already found out that times 45 over 2 degrees equals to 1 over x. This is according to equation number 1. So we actually have two different equations for times, two different expressions for times 45 over 2 degrees, 1 and 2. Therefore we created equation number 3 that states that tangent 45 degrees over tangent 45 over 2 degrees according to equation number 1 must be equal to tangent 45 over 2 degrees according to equation number 2. Tangent 45 over 2 degrees according to equation number 1 is 1 over x, and it must be equal to tangent 45 over 2 degrees according to equation number 2, that is square root of 2 minus 1. So in conclusion, we found out that according to equation number 3, 1 over x equals to the square root of 2 minus 1. Here we multiply this equation number 3 by x, and we found out that 1 equals to the square root of 2 minus 1 times x. Here we divided this equation number 3 by square root of 2 minus 1, and finally found out that x equals to 1 over square root of 2 minus 1. So x equals to 1 over square root of 2 minus 1. Here we multiply this side of the equation by square root of 2 plus 1, and then we divide it by square root of 2 plus 1. Square root of 2 plus 1 over square root of 2 plus 1 is 1. And it is allowable to multiply anything by 1. You don't change the value of the expression when you multiply the expression by 1. So this operation is allowable. So we multiply this side of the equation by square root of 2 plus 1, and then we divide it by square root of 2 plus 1. In the numerator we have, in this side of the equation, in the numerator we have square root of 2 plus 1, and in the denominator we have this expression square root of 2 minus 1 times square root of 2 plus 1. So this expression, what is the value of this expression? In order to find out the value of this expression, we implemented the algebraic identity that states that a minus b times a plus b equals to a squared minus b squared. According to this algebraic identity, we get that this expression equals to the square root of 2 squared, that is 2, minus 1 squared, that is 1. So in total, this expression equals to 2 minus 1, that is 1. So x in total equals to the square root of 2 plus 1 over 2 minus 1. That is to say, x equals to the square root of 2 plus 1, and 2 minus 1 is 1. So x equals to the square root of 2 plus 1 over 1. That is to say, square root of 2 plus 1 over 1 is square root of 2 plus 1. So in conclusion, we found out that x equals to either the square root of 2 plus 1 units in itself, or in terms of numbers, x equals to 2.414 units. I repeat again, we found out that the length of this line segment BC that is equal to x, it is equal to either square root of 2 plus 1 units in its length, or BC that is equal to x. In terms of numbers, it is equal to 2.414 units. Okay, thank you very much.